Hey guys, this is Ed with the Kaizen Effect, and today I'm super excited to be starting a new series of videos, which we're going to take a look at the orbits of our planets, and in particular, we're going to derive and prove Kepler's law. So what kind of questions are we going to be asking in these series of videos? We're going to ask questions such as, what does the orbit of our planets in the universe, what does it look like? What kind of shape does it exhibit? Is it a circle? Is it an ellipse? Who knows? How do you derive that? How do you even approach a question like this? Furthermore, once we know the shape, how do we characterize it? What kind of periods does it have? Right? How long does it take to orbit the sun? Okay, so in these videos, we're going to tackle these questions, and in the end, we're going to derive and prove Kepler's laws, and I'll go into them later in the series. But for now, in order to start this, I want to first talk about the history of how Kepler actually went about proving his laws and coming up with these theories and ideas he had. And then once we take a look at that, which I think is going to be very interesting because we're going to find that it actually didn't involve a lot of physics. It was a very geometric approach that I think is super beautiful. After that, we're going to take a look at an underlying philosophy and principle that is going to drive the structure we're going to develop and how we're going to set up the problem in this particular video. Okay, so first and foremost, first things first, what we're going to take a look at here is the history. How did Kepler come up with his laws? What was the general atmosphere like in terms of the universe, in terms of planetary orbits? What was going on back in the day? Well, back when Kepler actually proved this in the early 1600s, it was a time in which people thought that the circle was a heavenly, divine kind of entity. They thought that the circle, it was used for such beautiful inventions such as the wheel and other things, that it was something heavenly handed down to humanity that we have to honor. And hence, the heavenly bodies, which were symbology of God and, these higher beings, probably should have a circular orbit, right? So people were predisposed to believe that the planets would orbit around the sun in a circular fashion, okay? People wanted to discover that the orbits were circular, okay? So in this atmosphere, people also believed that the Copernican model that the planets revolved around the sun was subject. People didn't fully believe it. And in fact, Kepler's teacher, or rather the person he worked under, his main astronomer, actually didn't believe in this model, which is pretty interesting. Okay, so that was the kind of atmosphere that Kepler was doing his work in. And when he was very young, about age 27, he was working under a very wealthy astronomer known as Tycho Brahe, I believe that's how you pronounce it, who, again, didn't believe in the Copernican model, but what he was doing, he was an astronomer, he was taking a very close look at Mars. He was looking at how it orbited around the sun. Well, he didn't believe it orbited around the sun at the time, but that's what was happening. So he's taking measurements of Mars in the sky and recording that based upon our calendar. Okay, so he took very nice data, very precise data. And at first he didn't want to give it to Kepler because he thought, hey, if this guy gets this data, he might disprove the models I believe in, that we don't revolve around the sun. He might use it to prove the Copernican theory. I'm not going to give it to him. Well, fortunately for Kepler, what happened? One day, his wealthy astronomer he worked under actually ended up dying. So fortunately, he was passed down this information, passed down this precise data regarding the Mars orbit. And what Kepler decided to do was he decided, hey, I got this data. Let me see if I can figure out what is going on with the planets, what's going on with the orbits, and do something useful with that data, right? So, as I said previously, he was predisposed to believe that circular orbits described planetary orbits, okay? So he wanted to use that data to figure out that, oh, Mars is going around the sun in a circular fashion, okay? So he tried a long time to take all that data and show that it was orbiting around the sun in a circular fashion. But guess what? We know today that's not the case. So he found that he couldn't make the data fit to this circular model. And he was like, scratching his head, trying to figure out what the hell was going wrong. So one day, he was taking a look at the area swept out by a line connecting the planet and the sun, and he discovered that it didn't change with a change in time. This led to one of his laws, which we'll get into later in these series of videos, but what he found was that, well, the area is the same. So for that reason, maybe the sun changes, the planet Mars changes speed at different places around the sun. Well, what does that mean? That convincingly made him think that, oh my God, I want the orbits to be circular, but perhaps they're elliptical. Okay, so he tried to work out an elliptical orbit, and it turned out that converged upon the data, and that helped him come up with his other laws. Okay, so Kepler spent a lot of time trying to prove that the orbits were circular, took data, and through geometric means, solely geometric means, because we didn't have Newtonian mechanics, Newton actually took Kepler's laws and used that as the basis for his laws on gravitation. So he took geometric principles and this data from astronomy to figure out the orbits of our planets. Now, think about that really hard. That's absolutely brilliant. That's absolutely amazing. He didn't use any Newtonian mechanics. He didn't use any Lagrangian mechanics. He didn't use any physics as we know it in this day and age, right? That's absolutely beautiful. Then what happened was, once we had Newtonian mechanics and Lagrangian mechanics, people started looking at these problems, started using the physics as we know today, and they found out that his laws, which were derived intuitively through geometric means, through all this data, through astronomical data, were absolutely correct. That's absolutely amazing. That's absolutely mind-blowing. I think, that's super ingenious, super beautiful, super, super beautiful. So I want to share that with you and let you know that in order to prove Kepler's laws, the orbital motion of our planets, we actually don't have to use physics. We can use geometric means. Okay, so that's very, very cool. And as I say in other videos, if you want to be sure about what you're doing and check your work, find multiple ways of doing that. Okay, this is one example of that, and it illustrates it beautifully. Okay, so that's the history of Kepler. What we're going to do in this video and subsequent videos, we're going to derive those laws, derive his conclusions using the physics we know, and in particular, we're going to use the Lagrangian mechanics that we spend so much time putting together in my other videos and also my Udemy course. I have a Udemy course that trains you how to use Lagrangian mechanics. You can check it out by clicking the card right here if you wish to do so. But in this video, what we're going to do is we're going to start questioning what the orbits are going to be. How do we even approach that? How would you approach figuring out the orbital motion of planets? Okay, this is a pretty complex problem to ask. This is a pretty complex, convoluted question because we're dealing with gargantuan masses, gargantuan bodies with, very large orbits. And with a complex problem like this, what you want to do is you want to take a step back and question, how can I make this complex, convoluted problem as simple and straightforward as possible? Let me work efficiently, let me work effectively, and let's not kill ourselves here, okay? So that's going to be the driving premise in this course. But the philosophy we're going to use is that when you start approaching a physics problem, you want to think about your perspective, your perception of the motion. How are you looking at it? And furthermore, how is your perception of that motion affecting your structure, affecting your analysis, affecting your approach? Does it force physical quantities to arise in your analysis? Do you have to account for physical phenomena that you wouldn't have to account for if you took a different perspective, if you looked at the motion in different ways? How can you pick a perspective, a way of collecting your data and measurements such that you take the most efficient approach possible? Okay, so this is the underlying premise and the underlying principle in this video that we're going to tackle. And what I'm going to say is we're going to find that, as one of my lyricists, my favorite lyricist says, perspective pries your once weighty eyes and it gives you wings. I'm going to say that again. Perspective pries your once weighty eyes, and it gives you wings. What am I talking about here? Depending upon our perspective of the problem, of the motion, of how we look at the planets and how we analyze them, or in other words, in the language of physics, depending upon the reference frame we choose, that's going to drastically affect the ensuing emotion. That's going to affect our analytical approach. Sometimes it's going to account for physical phenomena, other times it's not, right? For example, let's take the example of Coriolis forces and Coriolis acceleration, okay? If we choose our reference frame in a way in which we're on a body that's moving, that has a constant angular velocity, what's going to happen is we're going to get this physical quantity known as the Coriolis force that helps account for that motion respective to our chosen reference frame. But if we chose a different reference frame, it won't prop up. For example, if we're on a merry-go-round and we have a baseball, we might be moving around at a constant angular velocity. We may throw that ball, and because we're moving around, let's say we're going in this direction, or what's the best way to think about this? Yeah, let's say we're going in this direction, so our angular velocity vector is in the positive z direction. So if we're going around like this, and we throw the ball like that, naturally it's going to be in a straight line, right? It's going to be in a straight line, but in our reference frame in that merry-go-round, we're moving like this. So if it's going in a straight line, it's going to look like it curves, right? And that's going to give rise to the Coriolis force. The Coriolis force is a function of our angular velocity and the velocity of the ball. So it's like a cross product, and it's going to account for that curvature. But if we looked at the problem off of the merry-go-round, we saw the person throw it, the ball is going to go straight. It's going to go straight. We won't have a Coriolis force. And that's because, again, perspective pries your once weighty eyes, and it gives you wings. If you change your perspective, it might open your blinders and make you become cognizant to different analytical approaches, maybe different phenomena in reference frames that you have to account for, you don't have to account for. However, if you choose your reference frame in a way that simplifies your life so you don't have to account for a ton of this stuff, so you don't have to account for physical phenomena, so you don't have to complicate your life, you can work efficiently and effectively, and you can get an analytical approach that, as the lyric implies, gives you wings, allows you to soar, allows you to have this analytical power to be in control of your analysis and work as efficiently and effectively as possible. This crops up all the time in physics, okay? You know, this is the premise of special relativity with Einstein, right? Einstein wanted to find some universal reference frame so we could relate quantities between different reference frames, and there was no bias between them, right? That's why he discovered principles such as time dilation, length contraction, and he found that based upon how you look at motion, we're going to get different measurements, but in the end, the laws of physics are consistent and universal across those reference frames. So your motion may look different, your equation of motion, your final solution may be different in certain reference frames, but they converge. They converge upon all reference frames. It still describes the motion. Einstein found that physics laws are universal. They crop up in any reference frame you choose, regardless of which one you choose. Okay? So the premise that is going to drive this video is that we're going to find that if we take certain reference frames, if we change our perspective, it's going to open our eyes to the potential and opportunity available to us and allow us to have more analytical power, soar, and get stuff done as efficiently and effectively as possible. Okay, so what we're going to do in this video, we're going to focus on the structure, the mathematics, and the underlying framework that is needed to derive the orbital motion found in Kepler's laws. We're going to tackle what is known as a two-body central force problem, and this philosophy I've been talking about is going to drive us forward in the problem. It's going to help us simplify what we're doing, and I want you to keep that in the back of your head, that if you choose a different reference frame, it might make the problem very easy, because we're going to find that we start out with 6 degrees of freedom with two bodies, right? X, Y, Z for two bodies interacting amongst each other. We're going to reduce that from two bodies to a one-body system with less degrees of freedom, just by being cognizant of our options for choosing the reference frames and choosing the one that works best with us, okay? So the next thing we're going to do, we're going to jump into the mathematics, and I want you to keep that in mind, and I'll show you when we're changing our reference frames and taking advantage of that and using it to make our analysis efficient and effective. All right, so now that you know a brief history of how Kepler's laws came about and you understand the underlying philosophy that's going to be driving our analysis to make our lives as easy as possible, what I want to do now is start considering how we put together the framework that's going to be used for deriving the orbital motion of planets in our universe. So, basic setup of the problem, and then we're going to start figuring out the geometry, what generalized coordinates we're going to use, and so on and so forth. Basically, the approach we generally take with Lagrangian mechanics. So, the system we're going to use to derive the planetary orbits is the following. We're going to use a two-body central force problem, okay? What that means is we're going to consider two massive bodies. Body 1, I'm going to call the sun. We're just going to use that for example. And body 2, I'm going to call the earth, okay? That's why it's green and the sun is red. My art sucks, but this will do the job. Okay, so we're going to have two bodies, and we're going to track their positions with regard to an origin. So we're going to have an origin here, and we're going to say the position vector R1 always points to the position of particle 1, and the position vector R2 points to the position of the Earth. Okay, now you might be thinking, what about, there are a ton of objects in space, other planets that can affect the orbits. What are we doing with that? That's a good observation. This is really like a first order approximation in a sense. It's definitely an approximation, and the other planets will affect this, but gravitation and the law of gravitation is an inverse square law. It's 1 over r squared, right? This is the force that's going to be between these bodies, which I'll get to in a second. You see this r squared at the bottom. Okay, so as a result, when things are far away, the force is minimal and it's essentially negligible. So this is going to approximate the situation we have in our universe, basically our galaxy, and what we're going to find is that it's going to do the job. It's going to help us derive the orbital motion that Kepler found. It's going to help us prove Kepler's laws and help us drive forward with the problem. Okay, so that's how we're going to set it up. And we're also going to define another vector, which I'm going to call the relative motion between these two bodies, these two planets. We're going to call it r, and it's going to be r1 minus r2. Now, if we do basic vector addition, when you subtract a vector, that points in the opposite direction. So when you do vector addition, you just go along the line. So if we go up to the arrow, we would come down here, and then it would look like this. So for that reason, it's pointing in this direction, right? That's why this is always pointing to object 1. So r, the vector r, is always going to be pointing to object 1. That's the convention we're going to use in this analysis. And it's in the math, inherent in the vector notations, okay? So, first things first. We got a simple problem. We got some geometry. We're going to have 6 degrees of freedom because this guy has to have an x, y, and z, and this guy has to have an x, y, and z. 6 degrees of freedom. What does that mean? If we have 6 degrees of freedom, what have you found in our other videos regarding Lagrangian mechanics? That means that we're going to have 6 equations of motion describing each coordinate. That does not sound nice. That's very complicated, very complex. So we're going to work to try to get rid of that if we can. But for the meantime, we're going to work with this convoluted setup and see what we can do with it, see what we can understand about the problem, okay? So we have these guys, and we know from Newton's law of gravitation that there's going to be a force between these guys that act towards the center, right? They act towards the bodies. That's why we have a central force problem, okay? So Newton told us that the force on body 1 with respect to body 2 is given as the following. Negative g, the universal gravity constant, the mass of body 1, the mass of body 2, over the distance between them squared. So we could put in this r vector. I'm going to leave it like such as of right now. And the unit vector we're going to use is going to be in the direction of that r vector. So this reads as the force on body 1 from body 2. So you would expect body 2 to pull this guy, so you'd expect it to be the right? R is pointing towards the left. So when we get the negative in line, it's going to say the force is in that direction, which agrees with our logic, agrees with our intuition. That's good, okay? You always want to double check this stuff. You want to be very strict with your conventions, with your negative signs. Pay attention to that because it can get very confusing very easily. Now, the next thing we want to do in any Lagrangian mechanics problem is usually you want to find your generalized coordinates. In this case, I'm going to assume we have the 6 I told you before, okay? Then what do? Then you sort of get stuck. If in terms of the information you have from my other videos, how would you proceed? We have a force, and you're probably thinking Lagrangian mechanics doesn't have any forces in it. And based on the information I've given you, that's sort of true. There's an alternate method known as the virtual work, which you can incorporate into your Lagrangian mechanics. That can get you forces into it. But what we know right now is that the Lagrangian is defined as kinetic energy T minus potential energy U, and that's used to derive our equations of motion. Well, we could figure this guy out using our generalized coordinates, but this guy, what do we do? We got a force. How do we get this force in there? What do we do? So I want to spend some time questioning that because we've never seen this before. And if it's basic, you feel free to skip ahead. I'm going to have a list of sections in the comment section. You're welcome to skip ahead to the next portion of this video. But I think this is very important. This is the first time we've taken a force and tried to get it into our system, try to get it into the Lagrangian mechanics approach. So my question for you, how do we do that? How do you think we can get a force into the nice setup we put together for Lagrangian mechanics? What can you do? Any thoughts? Well, we know that the Lagrangian is a function of our kinetic energy and our potential energy. And furthermore, we know from Physics 101 that the force can also be defined as the negative gradient of our potential energy. So we see we could take the force and relate it to U somehow, and that's exactly what I'm going to show you how to do, how to incorporate it into the analysis, okay? So we're going to use this, and we're going to revert it to figure out what U is. So basically, previously, what we did in a Lagrangian mechanics analysis, if we dealt with gravity, for example, we would have, some kind of ground, and we would have an object. We would bring it up. Basically, the direction we worked on was in the positive y direction, dr, and then we had a force of gravity that we worked against, which was mg going down. Now, what we did, we said potential energy is work. It's the amount of work you have to exert, the amount of energy you have to put into a system to work against a force or to work with it, which we'll see in this problem. And to define that, we just take the definition that U, or work, is simply the integral of f dot dr. And to account for conservative forces, we put a negative in there, okay? So that's what we found. And we knew that the dot product is basically f dr times the cosine of the angle between the vectors. So the angle, here it's 180, that gives us a negative, and this comes out as a positive, which makes sense, right? We're putting energy into the system because we're working against this gravity. We're pulling it up, in essence. So this just becomes mgh, where this is the distance h that we lifted the object, in essence. We put potential energy into the system. We gave it potential to do work, to do something valuable, to convert it into kinetic energy. Okay, so we're going to do the same exact thing. We're going to use this expression, but it's going to be a little different. The thing I want to point your attention to is that for this, we set this as the reference point. We set that as 0, and that's the point at which, the net force would be 0, because if we put something on the ground, it's going to be 0. We're going to have a normal force that cancels out. There's no motion down there. There's no potential to do work unless you get rid of the floor, and then it would fall, right? So this is based on our reference, and the reference is going to control the sign, okay? So what I want to do next is I want to use this concept with what we're actually doing in this problem at hand. Okay, so the problem at hand, we're trying to figure out the potential of a body at this position. So the potential for body 2, we'll use 2 for an example, is what happened was we could use a reference out in space, out infinitely far in space, because the force would be 0, right? So like our previous case, using that analogy, we can extrapolate from it, and we can incorporate it into our analysis. So we can say, okay, let's figure out the potential energy we have by bringing the planet from an infinite distance to this position R. Okay, what would that be? How do we do that? Well, in this case, it's different from the situation we had in which we're acting against the force with lifting it up from the ground, right? In this case, we have a body that, it has some kind of gravitational force that's pulling it towards body 1. And what we're doing is we're acting in that same direction. So you can sort of think about this as in our reference frame, which we're going to use as infinity, where the force is 0. That's basically when it had all of its potential energy. Okay, and then what happens is the potential energy gets converted into kinetic energy. It gets faster, and the potential energy is decreasing, okay? The potential energy is decreasing, right? So we would expect, when we pull this over here, that the potential energy with respect to our reference would be negative, right? Because it was converted into kinetic energy, right? So this jives well with our mathematics because, our mathematics says that if we have a conservative force F, and the force of gravity is a conservative force, what happens is we get this. So F dot dr, the cosine of that angle is 0, cosine 0. It's going to give us 1. And that's going to leave the negative sign out there. So we're going to get a negative, okay? So how do we actually figure out the U? Now, we could look this up. This is known. But in order to show you how to convert this into a potential energy, I think it's a valuable exercise to go through this. So what we're going to say is we're going to integrate the potential energy, how it changes from taking it from this reference point all the way over here to the position we have, okay? And the way in which we're going to do that is we're going to use the same definition, but we're going from infinity to position R, okay? So it's F dr. I'm going to use this little r in there. So I'm going to say, okay, this is negative g, m1, m2 over r prime squared dr prime. The only reason I'm putting that r prime in there is so we don't get confused with that variable there, which is going to represent this distance, but this r is going to be the distance from basically this planet to where it is out in space, okay? And we're going to vary that from infinity to r. So we're working with the force. We're taking our potential energy, converting it to kinetic energy. We would expect to get a negative, okay? So we can pull this guy out. We can pull out the constants. We get a g, m1, m2. Then we have the integral from infinity to r of 1 over r prime squared dr prime. Okay, so this is like r prime to the negative 2. So what happens there? Basically what happens is we get a g, m1, m2, and then we get negative 1 over r, okay? So this guy is going to be defined using these limits of integration. And what we find, and this is why we sort of chose our reference frame at infinity to be 0, or to be infinity, such that this guy is going to cancel. Okay, so what we end up with is G M1 M2 over R for that term, and then that affinity 1 over infinity is 0, so that cancels out. So we get U. I'm going to explain this for a second. That's our U, and that could be used with our Lagrangian, right? That could be used with our Lagrangian. So I'm going to write that guy up here. That's an important result. Is going to be defined as negative G, the mass of body 1, the mass of body 2, over R. And of course, we could take the negative gradient of that, and that would give us the same force here. But it's important to note that this potential energy, it's invariant to where we are in the z direction. So if this is x, that's y, and that's z, it's invariant to how the system moves. So, for example, if we change the coordinate to an s, and we took this whole system, maintained that distance, moved it out of the board a bit, guess what? That distance is the same, this quantity remains the same, and furthermore, this is only dependent upon the magnitude, right? This is a scalar quantity, it's not a vector. So what we learned from this is that we could take the force, we can do this analysis, and we can figure out what the U is, and that could be incorporated into our Lagrangian mechanics approach. Okay? And furthermore, this U is going to be a function of the distance between these guys. It's going to be a function of R, which is going to be very important in our analysis. And furthermore, it only depends upon the magnitude of that distance. Okay? Very, very important distinctions we've just made. Keep that in mind. Okay? So we took the force, we converted it to a potential energy. If you're ever working with Lagrangian mechanics and you get some weird force, you could take that approach to figure out how to convert it to a potential energy, how to represent that force as a potential energy, and as such, you can inject your force into the Lagrangian mechanics analysis, and that's going to allow you to do the same thing. So I thought it was an important exercise to run through this instead of just taking this value out of a textbook. This is a common result. A lot of people know this, and just using it. So if we pick these generalized coordinates and we know the U, kinetic energy is going to be very easy. What we could have done is we could have written down the Lagrangian and then figure out the equations of motion, right? So what we could have said is, okay, Lagrangian, that's easy. That's just 1/2. The kinetic energy of body 1 is 1/2 m1. That's R1 dot squared, basically the magnitude of that guy. And we add on the kinetic energy of this guy, plus 1/2 m2 R2 dot squared. And then we subtract the potential energy, so minus U sub R. Okay, so we could have done that. But what we're going to find is that that's sort of convoluted, because in order to proceed, right, we're going to have to consider Lagrange's equation for each generalized coordinate we accounted for, right? So that means we're going to have 6 equations of motion. It's going to be hell. We don't want to solve that, so we have to ask ourselves, or remind ourselves, perspective pries your once weighty eyes, and it gives you wings. How can I make this problem more efficient? How can I work more effectively? How can I change my perspective, change my reference frames, or change my analytical approach to eliminate all these cumbersome equations and come up with a more streamlined, straightforward approach? That's what we're going to tackle next. All right, so how do we actually do that? How do we simplify this problem and charge ahead with it? What I'm going to say is that we're going to take what we currently have, the Lagrangian of this convoluted problem with 6 degrees of freedom, figure out what we can understand from it, and then combine that with our previous knowledge, previous experience of physics, and try to come up with a new approach, try to come up with some new idea that we can try, right? So looking at this, we see that the main culprit here, the main problem is that we're using vectors r1 and r2. And those vectors each have 3 degrees of freedom, right? We need an x, y, and z for this guy, and an x, y, and z for that guy. So that's really introducing the complexity into this problem. But we also realize that this guy is very nice. The potential energy is just a function of this relative position between the objects. And we're going to find that, that's nice and easy. We can use that possibly as a generalized coordinate. What else can we use as our generalized coordinate? And what I want you to think about is another concept in physics that might inspire you to think of something else as a generalized coordinate. What do you think you would use? What would you use? Can you think of anything? No, maybe not. It's not super clear. Maybe you have ideas, maybe you don't. If you have a different approach, you can write in the comments section below, but the approach I'm going to take is, let's take a look at what we did previously for calculating kinetic energy of rigid bodies. Now, with rigid bodies, what we saw in physics 101 was that this guy, we can track the center of mass. We can figure out its linear or translational velocity, translational kinetic energy, which is the kinetic energy of its center of mass. And then we have to add on to it the kinetic energy of the mass rotating around that center of mass. Okay? That's what we did. So what we were able to do in that, let's say we had some simple linkage problem, like so. We had a guy going like that. And let's say the center of mass was right there. And let's say we had some omega, some guy like that rotating as such. So if we wanted to figure out the kinetic energy of this rigid body, what we had to do was figure out the kinetic energy of this guy and the kinetic energy of this mass rotating around it, okay? So that's what we had to do, and we found that we could do that exactly, or we could put the axis of this guy on the center of mass, and we would come up with all these different terms with respect to the origin, or we could put our axis at the origin, so we can keep track of this guy instead. And what happens, what we found is that when we do that, we don't have to calculate the translational kinetic energy of the center of mass. We would just calculate everything going around that because we changed our perspective. We changed what axis we chose to use. That gives us analytical power, right? We don't have to account for physical phenomena because if we choose the axis going through here, our I term in 1/2 I omega squared may change. This guy, well, it is going to change because our axis is going through here, not here. But if we put our perspective on this point, we won't have to account for the translational velocity because the axis does not move with respect to that origin, so that kinetic energy is 0. And what you find is that instead of calculating 1/2 mv squared plus 1/2 I omega squared, we just have to do this guy, and it greatly simplifies our life. So we see that from this, by keeping track of the center of mass, it opens up opportunities to simplify the problem. It gives us a chance to question what's going on here and how we can really change our perspective to increase our analytical abilities. So you might be thinking, okay, cool. Let's consider the center of mass, and that's what we're going to do. So we're going to take what we've done previously, take our experience, use the center of mass as a generalized coordinate in addition with the relative motion. It's sort of like the kinetic energy setup in the sense that we're keeping track of the center of mass and we're figuring out the motion relative to the center of mass. That's like what this guy is doing, the little r. And we're going to use that to make a difference, okay? So we're going to choose those as our generalized coordinates, center of mass, which I'm going to call big R, and the relative motion, which I'm going to call little r. So you must be thinking, how do we calculate the center of mass? You should know this. If you don't, I'll briefly review it. So the center of mass is sort of like the expectation value of the position of our mass. So it's like an average, right? When you hear expectation value, should trigger an average. So we're going to average the positions of these masses, and we're going to take a weighted average in terms of the mass. So the way in which we do that is we're going to say the center of mass R is going to be defined as M1 R1 plus M2 R2 over M1 plus M2, right? We're taking an average. If this doesn't make sense to you, you can think about it in terms of test scores. How do you take an average of test scores? You take the number of scores, you times by that score, you add them all together, and then you divide by the numbers you consider, the number of scores you considered, right? So the number of test scores is your weighting average. We're doing the same thing here. We're just changing the number of tests. So like, let's say we have two 80%. So we have 2 times 80% plus, let's say we have 3 90% plus 3 times 90%. Then we divide by 2 plus 3, which is 5. And we're weighting based upon the number of the scores we get. We're doing the same thing, but we're using the mass, right? Same setup, and we're trying to figure out the position as opposed to the average position of the mass as opposed to the average score. So that's one way of thinking about that, and that's the way we're going to use, okay? So we're going to use these coordinates, and I'm going to say that we can take M1 and M2, redefine it as big M, which is going to be M1 plus M2 to simplify our life a little bit, and I'm going to write that result right up here. So this is a vector, so backtracking a bit, we should have vector notation there. So I'm going to write the result up here in the correct fashion. So we get M1 R1 plus M2 R2 over big M. Okay, so you must be thinking at this point, well, that's great, but if we change our generalized coordinates, we got to figure out how to put them into our Lagrangian. So what does that mean? It means we need to define our geometry in terms of these coordinates. So we're going to have to redefine this quantity and that quantity to use R and big R. Right? How do we do that? Well, what I'm going to say is, I'm going to take this guy out, make some more board space. We're going to use our definitions. We're going to use this, and we're going to use this. So first, I'm going to use this guy, and I'm going to plug it into there. Okay, so what I'm going to say is that if we have R is equal to R1 minus R2, well, we could say, and I'm omitting the vector notation here, just so you know, we could say R1 is equal to, well, R plus R2. Okay, so we got one equation here. Cool. So, we have 2 equations we're trying to eliminate. 2 variables. We need 2 equations. We got one equation here. Let's see if we can use this guy right here. See what we get out of it. Okay, so I'm going to write that down. R is equal to M1 R1 plus M2 R2 over big M. Okay, so we could say, okay, that's not too bad. We can plug R1 into here. So this is just M1 times little r plus R2 plus M2 R2, right? Divide by that big M. Okay, now we need to group terms, and we want to try to get rid of the R2. Okay, so what we're going to do is we're going to say, okay, well, what we could say is we can, sorry, I was just looking at my notes really quickly. We can come down here, and we're going to say, okay, we have M1 over M of little r. Now let's group the R2s. Plus M1 plus M2. Basically, this guy plus that guy times R2. That's all over big M, right? Well, guess what? This guy is big M, and that cancels off that guy. So we have R isolated, And we can define R2 in terms of little r and big R very easily by just taking this guy over there. So I'm going to sort of flip the equation. We can say R2 is equal to big R minus M1 over big M R. Then we can put in our vector notation as such. I'm just going to check, see if I did the math correctly, which I believe I did. So we got R2. Yes, we got that right. So we're taking the algebraic approach. We could do a geometric approach, which I'll show you shortly. But let's stick with this. So I'm going to write that result right up here and then get more board space. So R2 is equal to big R minus M1 over big M little r, okay? Good job. So we got that guy. Now, you're probably thinking, okay, we need R1. Same approach, same algebraic approach we can use here. Erase the board, get rid of this garbage. Now we're back at square one. What can we do? What we could do is, okay, so what we did is we found R1 first, and that allowed us to get R2 because we defined this guy in terms of R2s, and then we isolated R2. Let's do the opposite. Let's bring this guy over here. So we bring R2 over there, we bring that guy over there. So that becomes R1 minus R. Okay, so we got this guy, one equation. We need to use that in here to isolate R1. So what we get is we get R, and again, I'm dropping the vector notation. We get R is equal to M1, R1 plus M2, R2 over big M. And we're just going to drop this guy right into this equation and see what happens. So this is equal to M1, R1 plus M2, R1 minus R. All that is over big M. So again, we're going to group the terms and then isolate R1. So this is equal to M1 plus M2, M1 R1 plus M2 R1 divided by big M. And then we're going to have this minus M2R over big M. Okay? So we can say, hey, this is M. This cancels out. Bam! We can isolate R1. So what we end up with is, if we bring this guy over and whoosh, flip the equation, what we get is R1 is equal to R plus M2 over MR. Okay? That's what we get. Double check my math. See if it's right. And it is. So we're good to go. So we got this result too, which I'm going to write up here. And again, I added in the vector notation at the end. Okay. So we define our geometry in terms of our generalized coordinates. And what we want to do is take these new definitions, plug them into our kinetic energy, and then chug ahead, okay? So that's the next step. But what I want to do is I want to take a moment to say, okay, what does this look like geometrically? And could we have done the same thing geometrically? I'm going to show you an alternate way of doing this. Again, it's the point of the philosophy in the beginning of this video was not to say this, but we're changing our perspective, we're changing our analytical approach. It might be easier, but if we can do it in multiple ways, chances are it's probably right. So let's do that. So geometrically, what is the center of mass? What does it look like? What's going on? So the center of mass, what I'm going to assert and then prove is that the center of mass is going to be always on this line between the two bodies. So I'm going to write that in, big R, and I'm going to put center of mass. Okay, so it always points to a point on the line connecting those two guys. And we see that R2 and R1 can have these guys here. So if we use vector notation, right, we can say R1 is just go from tip to point. R plus this guy. So this guy is a fraction of R. That makes sense. Intuitively, that makes sense, but how can we derive that? How can we figure that out? And furthermore, why is this always on that line? How can you prove that? Well, let's take a bit to actually show that. And what we're going to find is that this gives us a very nice way for redefining the coordinates very, very quickly without having to do a lot of algebra if we choose not to do so. So in order to show that, what we're going to do here is play some logic games. We're going to take special circumstances and figure out what we can deduce from those special situations. So what we're going to first say is we're going to suppose that R1, the vector R1, is 0. So x, y, and z are both 0 such that this particle gets squashed down to the origin. So when that happens, we sort of have to redefine what this looks like geometrically. So what's going to happen is we're going to have an origin here. I'm going to put an O. We're going to have particle 1 there. And then we're also going to have particle 2 like such. So this is going to be particle 2. R2 is still going to point towards particle 2, but we also have our little r pointing towards particle 1. So these lines are supposed to overlap. I can't really write that or else it'll look really weird, so I'm writing it as such. And what we're going to do with this special circumstance is we're going to figure out how that affects the center of mass and what we can deduce from that. So the center of mass is given as r, or rather I'm going to drop the vector notation to make our lives a bit easier, or rather mine. So it's defined as m1 r1 plus m2 r2 over big M. So if we set r1 equal to 0, this guy is going to drop off, and we figure out that this guy right here, the distance to the center of mass, is something like this, okay? So we see that this is always going to point towards that, but we also see that little r is equal to negative r2. So because it's in the opposite direction. Same magnitude, but it's in the opposite direction. So we could say r2 is equal to negative r, so we can get this guy. So what that means is that the distance from the origin to the center of mass is as such, and we see that it's always on little r. What does that mean? What does that mean? That implies that the center of mass is always going to be on this line connecting the particles, at least for this special circumstance. So that convinces us that asserting that the center of mass is always on the line connecting these two particles is pretty true. What else does it tell us? It tells us that the distance from particle 1 to the center of mass is going to be this fraction here, right? So we can say that this guy right here, pointing in that direction, is sort of like negative m2 over m r, right? Okay, so we get that result. And we can also do the same thing if we consider what happens if we squash particle 2 into the origin. So we're going to do that also and see what we can deduce from that information. So we're going to suppose that R2 is equal to 0. So in that case, I'm going to make this more pronounced so you can see it. So it might look a little different from our main picture, but what happens is we're going to have our origin O, and then we're going to have a particle 2, then we're going to have a particle 1. So this guy, we're going to have R. R is always going to be connecting particle 2 to pointing towards particle 1. So this is going to be R. And in this case, it also coincides with R1, right? Same exact thing as R1, because R1 is defined from the origin to 1, R is defined from 2 to 1, particle 2 to particle 1, or planet 2 to planet 1. So we also have a center of mass, which I'm going to define as such. And what we can do is we can question what happens with the center of mass once again. So we can say R, drop the vector notation. I keep doing that, bad habit. So that is just equal to M1 R1 plus M2 R2 divided by big M. We're setting R2 equal to 0, so this guy pops out and we get another fraction. But in this case, we have little r is equal to R1. So what we could have said is instead of R1, we could just replace it directly with R. So the distance from particle 2 to the center of mass, again, is a ratio of the mass times this R component, and that gives us this vector right here, from that to that. So this just becomes M1 over big M times R, okay? So what this tells us, this analysis, is that we get these terms that look very, very similar to those in here. Well, can we go any further with this? We found that R, the center of mass, is going to be on those lines in this special case, convinces us it's always going to be on that line. And what we can say is that, okay, we can redefine R1 and R2 geometrically using this knowledge. Maybe that's easier than doing algebraically. And it further convinces us that our result is correct if we get the same idea, right? So how do we do that? Well, we can say using vector addition, R1 is going to equal R minus this vector because it's pointing towards here. We want to go there, right? So if we do that, we just get, well, okay, R1 is equal to R minus negative M2 over big M, little r. Guess what? That becomes plus. Well, bam! They're both the same, right? Awesome. We got a different approach. Our perspective pries our once weighty eyes and gave us wings. We can do the same thing with R2. We could say R2 is equal to tip to arrow. If we want to go to that, we have to invert that vector because it's pointing this way. So we would have R minus this guy, M1 over big M, little r. Guess what? Well, bam! It's the same exact equation. So we got the same result using an alternate approach, a little bit easier, but the fact that we got it twice convinces us that we're correct and we can charge ahead in the problem. So this was not the intention of the problem again, but changing our perspective, changing our analytical approach, changing how we tackle the problem gave us an easier solution, okay? We're going to find that cropping up again and again and again in this analysis, especially when we change our reference frame, which is going to be coming up soon. But what do we want to do? We redefine the problem in terms of these generalized coordinates, big R and little r. What we need to do is finally transform the rest of the Lagrangian mechanics such that it is only in terms of little r and big R. That's what we're going to do next. All right, now that we have the generalized coordinates, R, big R, and little r, and we redefined these other coordinates, these natural coordinates with respect to the origin, what we want to do is we want to chug along in our recipe I gave you both in my previous videos in my Udemy course, which you are free to check out by clicking the card right here. I walk through all the Lagrangian mechanics and show you how to put together some super awesome simulations similar to those you'd find in video games. But anyway, back to the topic at hand. Now that we have these generalized coordinates, we want to continue with that recipe. That involves transforming our kinetic energy to be in terms of big R and little r using this definition here. Okay, so how do we do that? How do we do that? So for the kinetic energy, that's 1/2 mv squared for both of these particles. That's the total kinetic energy of our system. So what we found when we were defining the Lagrangian previously is that T is equal to 1/2 m1 r1 dot squared. That's basically the magnitude of the velocity of that guy there. And we had the kinetic energy, 1/2 m2 r2 dot, the magnitude of that squared, particle, or rather planet 2, mass 2. So what we need to do now is we need to plug these guys into here, and you must be thinking, there's a dot there, buddy. What do I do with that dot? Well, you know what? We could just take the derivative. We take the derivative on both sides. These are constants, they pop out, and basically we get the following. Bam, 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 ba-bam. So we get that, and we could plug them in directly, and I'm going to drop, especially since we have the magnitudes here, I'm going to drop the both the magnitudes and the vector notation, but this is essentially what we're doing. It's just going to be a lot of algebra. I don't want to cumber our board and cumber your learning ability. So what we're going to do is we're going to say, okay, I'm going to plug this in. I'm going to redefine this guy in terms of this and this only, nothing else, okay? So when we plug in R1 dot, we get 1/2 M1 big R dot plus M2 over big M little r dot. That quantity will be squared, and then we do the same thing with the second guy over here. So for R2 dot, we're going to get R dot minus M1 over big M R dot squared. Okay, so that's what we get, and all we have to do is just work through the math. It's not nice, but we're just going to do it, okay? We're going to chug along, we're going to have discipline, we're going to make it work. So, we get M1 R dot squared, we see that squared, plus 2 M2 over big M R dot little r dot plus M2 squared over M squared little r dot squared. Okay? Not too bad, not too bad. So now we want to repeat the whole process with this term. So what do we get when we square the terms? We get the big R dot squared. We're going to get minus 2 M1 over big M, big R dot, little r dot. Then we're going to get plus M1 squared over big M squared, little r dot squared. Okay, so that's what we get. And now we want to start grouping terms, canceling terms, and figure out what we essentially get, okay? So first of all, what we see is that this half is going to cancel with the 2's, so this term we would get M1, M2 over big M, big R dot, little r dot. Well, guess what? Over here, the half cancels with the 2, and we get negative M1, M2 over big M, similar to this one, big R, little r dot. So just naturally we see, bam, this guy drops out. We can cancel that naturally. So we only have to deal with these other terms in place here. And what we're going to find is that we end up with the following result. We get 1/2 M1 R dot squared plus 1/2 M1 M2 squared over big M squared little r dot squared plus 1/2 M2 big R dot squared. I'm just running through the problem, distributing, baby, plus 1/2 M2 M1 squared over big M squared R dot squared. Okay, so we see we have like terms here. We can add the M1s and M2s. So we get 1/2 M1 plus M2, pulling out the common terms, R dot squared. Well, does that look familiar? Of course it does. That's our definition of the total mass of the system. So we can say, okay, I'm just going to get rid of that, skip a step, be proactive here. So we get that guy, that term there. And then we could group these guys here somehow. So we get plus 1/2, 1 over m. We get m1, m2 squared plus, how do we want to do this? I'll pull out the m2, m1 squared, little r dot squared. Well, what if we do this? What if we do this? We could say, okay, this is 1/2 big M, big R dot squared. We could pull out, how can we do this? M1 and M2 plus 1/2 M1, M2 over big M squared. So if we pull M1 and M2 out of this, we get an M2, right, for that term. If we pull M1 and M2 out of this, we're left with an M1, right? So we get this little guy here. And you might be thinking, okay, we could do the same thing we just did, right? We could say, okay, this is just big M. This is big M. And we can cancel it with this guy. So in the end, creating board space, we find that the redefined kinetic energy is 1/2 M big R dot, the magnitude squared, putting in the vector notation again, plus 1/2 M1 M2 over big M R dot squared. Now what I'm going to say is, or what I'm going to ask you is, what in the world is this guy here? That M1 M2 over big M. Does that look familiar at all? I hope it does. Depending on how far you are in physics, you may have seen this before, you may have not seen it before, but this guy pops up all the time. This is defined as the reduced mass mu. It has the symbol mu. Okay, so we're going to say this is mu, where the reduced mass is M1, M2 over big M. And checking my notes, I think this looks good, probably is going to be good, but just to make sure, yep, we are good. So, what we find with the reduced mass is that, let's say we have M1 really big. If M1 is really big, this big M is M1 plus M2 is pretty much M1, so we end up with M2. Okay, so the reduced mass plays little funny games with you. You might want to play around with it, try out different values if you've never seen it before. I'm assuming you have, so we're going to proceed. So we get this nice result here, which I'm going to write down in our collection of equations as the kinetic energy is equal to 1/2. And again, this should be the magnitude of the vector. 1/2 M R dot magnitude squared plus 1/2 mu R dot squared. Now that's a very interesting result. So it's like the kinetic energy of the center of mass with a mass of the system. So it's like congregating the mass at that center point. And we also add on this fictitious kinetic energy of the reduced mass. So it's looking pretty interesting. So once we have t, and we already have u, which is a function of little r, what's the next step in Lagrangian mechanics? The next step in our recipe, and again, I don't like you thinking of it as a recipe, but this can be a guide, because when you start having recipes and you start doing stuff automatically, getting on autopilot, you tend to make mistakes, and furthermore, you can find more in the recipe as opposed to your own self, which I do not like. But the next step you would do in Lagrangian mechanics is you'd say, okay, let me figure out what the Lagrangian is going to be. The Lagrangian is always defined as t minus u. Okay, so we know that the Lagrangian is going to be 1/2 big M big R dot squared plus 1/2 mu little r dot squared minus u sub r. So what I want to point your attention to is the following. What we have is a Lagrangian in terms of our center of mass, right? It's only in terms of big R. And we also have this guy here, which is the Lagrangian with respect to the relative position, little r, right? We only need that to define that. So what's really cool is that we used our intuition to get the same result. Like what, I guess, inspired us to use the center of mass and this relative position was our calculation of kinetic energy, in the sense that we found that we could track the kinetic energy of the center of mass, and then we also had terms that revolved around it that also gave us rotational kinetic energy. And we're sort of saying the same thing here in the Lagrangian. We've separated it into two terms, a center of mass term and a relative motion term. So we're getting some headway. It looks like we're falling into the same system. It looks like we're making the same progress. That's super good. Super, super cool. So what we could do is we could take a look at the equations of motion. And what I'm going to say is that this is not going to be the final form we're going to use. We can further simplify this. We have not done the main point of the exercise here. I said the main driving philosophy is that perspective pries your once weighty eyes, and it gives it wings. What we're going to find is that working through this, thinking a bit, changing our perspective, change how we observe the motion, we're going to further simplify this, and we're going to get rid of the two-body problem and reduce it to a one-body problem. But, it's important to realize that we have sort of like a term for one particle at the center of mass with the total mass of the system, and another term for the mass that is revolving around that, okay? Very important distinction. Think about that when we're going forward. And next, what we're going to do is I'm going to convince you why we should change our perspectives and how we're going to do that. So what can I exactly do to convince you that we can further simplify this and guide your intuition towards choosing a new reference frame that drastically simplifies our analytical approach? What can we do? What I'm going to say is we can further chug along in the Lagrangian mechanics method, the approach we're going to take, see what happens, what information we can discover. And what I'm going to say is that's going to convince you that we can make a change, that we can change our perspective, open our blinders, and become cognizant to a new analytical approach that simplifies our lives. Okay, so what are we going to do? We're going to run along with the Lagrangian mechanics method. And how do we do that? Once we get to Lagrangian, what we need to do is figure out Lagrange's equation for each coordinate that we're going to specify. So in essence, what we have to do is we can consider each generalized coordinate. So let's consider big R first. So for big R, what we find is that the Lagrange equation is going to be the partial of the Lagrangian with respect to our path variable. In this case, it's big R. And that's going to be equal to the normal derivative with respect to our independent variable, time in this case, of the partial of the Lagrangian with respect to the derivative of the path variable. So what we find when we do this is something special. There's something special about this equation. The thing we find is that the Lagrangian is independent of big R. We don't have that popping up. We only have R dot, right? So this guy becomes 0. And this just becomes, the derivative ddt of this. So when we take the partial with respect to r dot, the 2 comes down, we get m r dot, big M r dot, and this is just equal to big M r double naught. In other words, it's an equation that gives us Newton's second law, F equals ma, for no force acting upon it, right? But what's really interesting is we get an equation for the center of mass with the total mass, like a big particle with the total mass at the center of mass. What I want you to focus on is what happens when we try to solve this. What happens if we divide by m, because we got 0 over here, and we integrate? What we're going to find is that, and this is an important result, is that r dot is a constant. That's pretty interesting. Very interesting result. What this means in a general sense is that the r coordinate is ignorable, or some people also call it cyclic. So that means that we get a 0 on this side, it's constant, and in essence, we don't have to account for this. This is going to be a pivotal piece of information when we make that change of perspective, which I'm going to go over in a bit. So keep this in the back of your head, but I want to go through with the little r equation. So we're going to do the same thing with little r. Basically, the partial of the Lagrangian with respect to the path variable is equal to the derivative of the independent variable with respect, or rather the derivative of the partial of the Lagrangian with respect to the little variable dot. Okay, so in this case, we do have that guy. So this is sort of like the partial. So I'm going to write that down as, or rather the gradient. The gradient of u is equal to ddt. So in essence, backing up a bit, we just looked through the Lagrangian, found that this is, in terms of r, we had to take this guy, which is a part of the gradient. So I just wrote the full term down, the full vector quantity there. Okay? And so we got this guy. And next we want to find the partial with respect to r dot. This is the only term with r dot. 2 comes down, we get mu r dot. I'm going to drop the vector notation with that. So we get, or rather I'll keep it. It's not that bad. So we get r dot. And then we have to take the derivative, so we end up with mu r double dot. Now, what we find is that, again, this is Newton's second law. F, remember F, we saw at the beginning of this video, is the gradient of u, right? F is the negative gradient of u. So this is like the sum of the forces equal to m, a particle of mass, reduced mass, mu, times the acceleration of the relative motion. Okay, so this is like having a single particle of mass mu, position r, and potential energy of u sub r, and this is the equation we end up with in essence, okay? So I'm going to actually put a little r there. Now. Going back to this, if r dot is a constant, what can we say? Think about that for a minute. Think about that. Think about it. In essence, what we can say is this guy is constant. It's constant. So what if we lump this into there and redefine the u? Nothing would change. Nothing would change. Because this, in essence, is a statement of conservation of momentum, right? And we know that's true no matter what. We know that's true. We know that the momentum is m r dot. And the momentum is constant. So if the momentum is constant, this is pretty much useless. And that's why I called it an ignorable variable. We could say it's constant and lump it into here. That's sort of the mathematical approach. The physical and intuitive approach I want to take is asking the following. Using this information, can we redefine our perspective? Can we measure things in a different reference frame? What would happen? Well, what happens if I say, okay, remember with the kinetic energy, we were changing the axis from the center of mass to the origin? What if we change our perspective, instead of perceiving the motion, instead of viewing the motion, collecting our data from this origin point, what if we say, okay, we're going to move with the center of mass? What if we change our perspective so that we measure everything from this point, the center of mass? The center of mass is constant. The velocity is constant. So that's pretty easy to do, right? That's pretty easy to do. So what I'm going to say is that, what if, and I'm going to erase all this, what if we do that? And in order to do that, we have to do the following. We get the following result. How do we get that? We're going to say the velocity is 0 because this guy, let's say it's moving and then circling around. If we move with the center of mass, so, we're looking at these guys going like that, it changes our perspective, but the center of mass, with respect to us on the center of mass, it's not moving anywhere because we're currently at the center of mass. So we can also say this guy equals 0. And if we're moving with the center of mass, according to us, it'll look like the center of mass is not moving because we're moving with it. We're moving with it. Okay? Another way of thinking about this is if you're in the car, you're going, 20 miles per hour, let's make it more, 50 miles per hour, okay? And you have a drink in your hand. You're driving. From your perspective, it looks like the drink is not moving forward, but in essence it is. But from your perspective, the drink has a 0 velocity. You are contingent, or rather, you align with the position of that drink. So it's not moving. It has no velocity with respect to you. But from somebody else on the street, somebody else at the origin, it still is moving. It still is moving. But when you implant yourself in the reference frame that is moving, and you move at the same speed as it, your measurement of that same quantity, that same position, is 0 because you are moving with it. You are at the same position. So for that reason, we can assert that from this perspective, if we move at the center of mass, it's not moving according to us, according to our reference frame. So I said at the beginning of this course, or this video, that perspective pries your once weighty eyes and it gives you wings. My next question for you is, how did it pry your once weighty eyes? Well, we were ignorant of the fact that if we were at the center of mass, we could increase our analytical pries efficiency and effectiveness. So what do we get from doing this? Well, if we set this equal to 0, the Lagrangian gets redefined. Mathematically, this is sort of getting lumped into the U, and it gets redefined, but our Lagrangian then becomes 1/2 mu r dot magnitude squared minus u sub r. Isn't that amazing? Think about that for a second. What just happened? What just happened? Think about it. This is a very big point. We reduce the problem down from a two-body problem to a one-body problem. How do we do that? This happened because we only have to consider one particle with mass mu and one position r. So we drastically simplified this problem. We went from 6 degrees of freedom down to the 3 for that guy. Because we need 3 coordinates to define that. And since we only have one generalized coordinate in here, we're only going to have Lagrange equations for those 3 coordinates for r. Basically rx, ry, and rz. So in the end, if we do what we did previously, the Lagrange equation is just the following, which we just did, right? In essence, we ignore the big R, right? That's why it's an ignorable coordinate, right? So this is just what we found previously. We already did that, right? We already did that. This is the negative gradient of u sub r is equal to mu r double dot, right? Right? F equals ma for one particle of mass mu with one coordinate, little r, okay? So what did we learn? What did we learn by running through this exercise? Now, we put together the framework we're going to use for figuring out the orbital motion and getting these equations of motion for these two objects, these two planets revolving around one another. But we also found that if we're cognizant of our perspectives, how we take in information, how we measure and analyze the world around us, it can drastically affect the physics, the mathematics, the framework, and the power of our analysis. By taking a step back when we have hard problems and taking a new perspective, we can either eliminate complexity or we can introduce it to the problem. But we found one way to really replicate this simplification of this analysis, and that's if we have an ignorable coordinate, as such, you can do this. You can do this simplification. You can take a two-body problem down to a one-body problem and simplify your life. This is why perspective pries your once weighty eyes, and it gives you wings. It opens your eyes to what's possible, to what you can accomplish, to the power inherent in what you're doing, and raises your standards, raises your analytical abilities, raises your effectiveness, and raises your efficiency. Next, what we're going to do in the next video, we're going to take a look at angular momentum and figure out other ways how we can further simplify this and get an even better analytical approach. Hope you enjoyed the video. I'll see you next time.